Good morning. Today we will learn about frequency spectrum using DFT. We have already studied that DFT is an important tool in digital signal processing. It has got many uses. One is to calculate a signal's frequency spectrum. This is done by the direct examination of information encoded in the frequency, phase, and amplitude of the component sinusoids. That is, frequency spectrum can be analyzed using DFT, and this is done by examining the information contained in the frequency, phase, and amplitude component of the signal. For example, human speech and hearing use signals with this type of encoding. Now, this session is very easy to learn, so I have elaborated the lesson. So I think when you go through it, it will be easy for you to understand. Okay, so let us begin with an example. Suppose that you want to investigate the sounds that travel through the ocean. So first what you do, in order to collect the signal, we use a microphone, and the signal thus collected will be amplified to a reasonable level, and then we use a low pass filter to remove the unwanted frequencies, or to remove certain particular frequencies, and the signals, that particular signal is then sampled at a specific sampling rate. Then what will you do next? So you are collecting the signal using a microphone, then you are amplifying it to a particular level, then remove the unwanted frequencies using a low pass filter, then sampling it at a specific sampling interval. Now what will you do next? That is our question. So first, what you do, naturally you will examine the signal. That is, you will examine the measured signal. Measured signal, that is the signal that you get from the microphone after all this process that I have told, is shown in figure A. So you can see figure A here. This is a figure A. So here it is very evident that this contains a lot of noises. Okay, so this noises will not be sufficient for us to give the required information. So in order to remove the noises, what we do is that we multiply this measured signal with a smooth curve called Hamming window. Okay, called smooth curve called the Hamming window, and the resulting output will be a Hamming window as shown in figure B. So we are multiplying the measured signal with a smooth curve called Hamming window, and the resulting signal will be like this windowed signal shown in figure C. So in order to remove the noise from the measured signal, we multiply it with a smooth curve called Hamming window, and the resulting signal is called a windowed signal as shown in figure C. Now this figure shown in C is then subjected to DFT. We are applying this discrete Fourier transform to this windowed signal, and then we represent it, or we convert it to a polar notation, and the resulting signal is shown here, that is in figure D, which is a single spectrum. This is what you get. So before that, let me tell you one point. When compare these two figures, figure A and figure C. In figure A, you can see lot of noise, but in the windowed signal, towards the end, the amplitude is getting reduced. See, that is how there is a decrease in the amplitude when compared to the figure A. Here, amplitude level is high, whereas here the amplitude level is low. Okay, so up to this, hope you understood. You get the single spectrum. So I will explain it once again. You are collecting the signal, and then that collected signal is underwent a lot of process, which I have already mentioned, and you get a measured signal. This measured signal contains a lot of noise. To reduce that, we multiplied with a smooth curve called Hamming window, and the resulting signal is called by the name windowed signal shown in figure C. This windowed signal is subjected to DFT, and then it is converted to a polar notation, resulting in the final single frequency spectrum as shown here, this one. Okay, now observe this figure. Here also you can see a lot of noises. Okay, so in order to trap information from this, it will be very difficult. So One method that they have suggested is to use a long DFT. That is, in order to use a here we are speaking about a 256 point DFT. Now here increasing the number. This is all just examples. We are using a 2048 point DFT. That is, you are using a longer DFT in order to reduce the noise. But this doesn't have much effect. Why? Because if you use a longer DFT in order to reduce the noise, anyway the frequency resolution will be good, but the noise level will remain the same. So that particular technique was not effective. That is, using a longer DFT to reduce the noise was not effective. Why? Because if you use a longer DFT, frequency resolution will be good, but noise level will remain the same. This is because the more the number of points in the DFT, then greater will be the number of samples and your resolution will be good, but it will dilute or it will reduce the information content by the same factor. Why? Because this noise will be increasing. So using a longer DFT to reduce noise is not a good technique. Then what else can we do? So that was our next question. The suggestion put forward was that to use more of the original signal in such a way that increasing the number of points in the frequency spectrum in such a way that it does not increase the number of points in the frequency spectrum. So that was one suggestion put forward. That is, you don't have to use a longer DFT. Instead, you can use more of the original signal itself in such a way that it will not increase the number of points in the frequency spectrum. Now, how this can be done? This is the next question. So this is done by breaking the original signal or the input signal into segments, and each of these segments is multiplied by the Hamming window, and then the similar procedure, it is subjected to DFT and then converted to Polar notation. So that was a good suggestion put forward. So what was the first method? First technique that we used, the whole signal was subjected to the Hamming window, right? But here, instead of putting the whole signal into the Hamming window, what we do, we break that original signal into a lot of segments, and each of these segments is subjected to Hamming window, or each of these segments is multiplied by Hamming window. In the earlier case, we were subjecting the signal as a whole. We are subjecting it to the Hamming window, right? Here, instead of subjecting the whole signal into Hamming, or instead of subjecting it the whole signal into Hamming window, we are breaking that original signal into segments, and each of the segments is subjected to the Hamming window, and you will get a windowed signal, and then the same procedure is applied. That is, it is subjected to DFT and then converted to Polar notation. Then you will get a signal. That resulting signal is then averaged. One more step we are performing, we are averaging it, and the final one will be called as the average spectrum. So this average spectrum, it also, here you can see in the average spectrum, the noise level has been reduced to very low, has been reduced to a very low level. That is, there are not much zigzag peaks. So noise level is highly reduced. That is also, instead of using a longer DFT, we have reduced the noise level by how? By breaking the original signals into number of segments, and each of the segments is multiplied by Hamming window to get the windowed signal. The windowed signal is then subjected to DFT and converted to Polar notation, and finally we averaged it also to get the average spectrum. This average spectrum contains noise level very low. See, the noise has been reduced to a level very low level, and this reduction in noise is proportional to square root of number of segments. So we have discussed about two methods. So the first method, I will tell once again. The first method was we obtained the signal by using a microphone, and then we have amplified to a particular level. Then using a low pass filter, we have removed all the unwanted frequencies. Then we have sampled it to a sampling particular rate, and we get a measured signal. This signal as a whole is subjected to or it is multiplied. Not to remove the noise, the whole signal was multiplied using a Hamming window to get a windowed signal. This windowed signal is subjected to DFT and then converted to Polar notation. but we noted that the resulting single frequency spectrum contained a lot of noise. So how did we overcome that noise? We talked about using a longer DFT, but that was not effective. Why? Longer DFT will increase frequency level resolution, but noise level will be the same. So what we opted for, instead of subjecting the whole signal to multiplying the whole signal with the Hamming window, we have what we have done, that whole signal is we have breaked it into segments, and each of these segments is multiplied with the Hamming window to get the windowed signal. This windowed signal is then subjected to DFT and converted to polar notation. The resulting signal is then averaged to get the average spectrum, and from that we noted that the average spectrum, in the average spectrum, noise level was very low. Okay, so that was the first method, and here we didn't make use of any filter. The other thing is that suppose if we are using a long DFT, definitely it will have noise. So in order to filter out that noise, we can use digital filter. That is the second method, that is using a longer DFT, and then definitely it will have noise, and then filtering that noise using a filter. But the first method, that is instead of using that long DFT, we have talked about a procedure which I have just mentioned. That is called the first method, and that is very simple. Why? Because we are not making use of any filters. This is the steps I have just summarized, which I have already told. So please go through that. Now we are analyzing the signal that we have got. See, this is a particular signal level we have. Suppose that this is a measured signal that we got from the microphone after doing all these procedures. Okay, here we are looking about various types of noises. Here we can see random noise, or it is called white noise, and this is mainly seen between 10 and 70 hertz. It is called white noise because it contains equal amount of all frequencies similar to that of a white light. Then it arises from noise on the time domain, and it will not have any relation from one sample to another. That is, the noise level present in one sample will not give us any information about the noise level present in the other sample. So between 10 and 70 hertz, what is present? White noise is present. Then it is originating from several sources, and then other one is noise is below 10 hertz. I'm speaking about this particular figure, this one. Okay, so below 10 hertz, that is in this region, we can see a 1 by f noise or 1 over of noise, and it is measured in very diverse systems, and such as traffic density and all. And now we can see some sharp peaks. See, one at 60 hertz and the other at 13 hertz. Now we are going to speak about those sharp peaks. Okay, now at 60 hertz we can see a sharp peak, and it is a result of electromagnetic interference. And then we can also see some smaller peaks at multiples of 60 hertz, that is 120, 180, 240 hertz. And then we also can see some interfering peaks between 25 and 40 hertz, and arising from nearby radio and television stations. And finally we can also see some low frequency peaks between 10 to 100 hertz, which arises from the vibration of components present in the system. And these low frequency peaks are also called by the name microphonics. So while writing about these noises, just refer to the figure and write. Okay, then there is the most strongest peak here is at 13 hertz. Look at the figure, and that is called as the fundamental frequency. Now the weak peaks at 26 hertz and 39 hertz marked in the figure are called by the name second harmonics and third harmonics respectively. That is the analysis of the frequency spectrum. And finally, there are two factors that decide the resolution of two peaks. That is, resolution means how close the peaks can be without getting overlapped. One factor is the length of DFT. The frequency spectrum produced by an n-point DFT consists of n by 2 plus 1 samples. Okay, n is actually the length of the DFT. And so in order to separate two closely spaced frequencies, the sample spacing must be smaller than the distance between the two peaks. That is the condition. Please learn it. And so the longer the DFT, the better will be the ability to separate closely spaced peaks. Here this is clearly shown in this example. Here we are using an 128 point DFT and a 512 point DFT. This 5.1 5 512 512 length DFT has resolved the two peaks very clearly when compared to a 128 point DFT. This is highly resolved because length of DFT used is high. Here resolution is poor, length of DFT used is less. That is, a longer DFT will have higher ability to separate two closely spaced peaks. Okay, this is a little bit lengthy session, so we cannot cover it in one class. So this will be continued in the next class. Okay, hope this will be very clear to you once you go through it, because I have written it, I have taken it from very simple textbooks which you can easily follow. So please go through it, and we'll continue with the next session and the next class. Okay, that's all for now. Thank you.